Stream temperature has been noted to be a primary driver of aquatic ecosystems in that it affects where you can find organisms in the ecosystem and as well as the abundance of those organisms. Warmer stream temperatures are going to adversely affect cold water fishes like salmonids, and it affects them by changing their migration times, by changing their growth rates, by making them more susceptible to disease and predation. These effects are even more egregious when the water temperatures reach a critical threshold, which is different for each life stage and different for each species of fish. But we won't go into that today because that's just a little more complex than what we're analyzing. So some background on our study area. Many of the streams in the Tualatin and the Yamhill are already impacted thermally relative to the Oregon water standard of 17.8 degrees Celsius. And temperature is regulated in some of these streams as a water pollutant. And because of that, there's a lot of interest in mitigating stream temperature pollution, and some of the means of doing that are currently happening are increasing riparian areas and managing land conversions, as well as managing runoff or discharge that might happen from stormwater events, sewage plants, and power plants. So we created our model using ArcSWAT, which Wes mentioned. SWAT is Soil Water Assessment Tool, and it uses the inputs of climate, land cover, soil, elevation, and hydrology to create a watershed model. We essentially used an improved SWAT model that was created by Darren Ficklin's group. It's called SWAT Temp. And so the main difference between the two models is that the original SWAT model just uses a linear relationship with air temperature to estimate what stream temperature will be, and the SWAT temp model uses components of hydrology like snowmelt or timing of snowmelt to help better estimate what stream temperature would be. So you can see these are just some results of our calibration of our SWAT temp model. So we used observed data from USGS gauges that were inside the basins for the longest range of dates that we could find to calibrate this model. So that was basically 1981 to 2010. And you can see that the stream temperature model does a pretty good job of estimating or simulating stream temperature relative to observed temperature. It's got a bias of about 10%, at least as far as this model is concerned, and it's underestimating slightly in the summer months, and then kind of overestimating in the other months of the year. But overall, it's a fairly good fit. So just to reiterate, the climate scenarios that Wes already explained, we're using the same scenarios, basically a low, medium, and high scenario. And if you just take a quick look at the image here, you can see that the low scenario is changing the annual precipitation by about a little over 5%, and changing the annual temperature by a little, it looks like a little over than 1%, and that's compared to the high scenario, which is changing the annual precipitation, looks like just maybe it's 1%, and then changing the annual stream, or the annual air temperature by over 2.5%. Of course, as Wes showed you, that varies throughout the seasons and spatially, but I'm not really going to explain that here. We're into the results, or the preliminary results portion of our analysis. Most of the next few slides are going to kind of look the same as this, so I'll just let you know how they explain to you how they're set up before we move on. So we've got the legend at the top here, and then underneath we've got maps of the spatial distribution of the stream temperature results, and they're in order of increasing climate, so historic to low to medium to high. And this is for the entire 30-year study period. So for historic, that's 1981 to 2010, and then for the future climates, that's 2035 to 2065. So we're looking at the mean monthly summer stream temperature. We called summer June through September. And you can see that there's a low of 13 degrees in the upper reaches of the Tualatin here in the historic model. And then we get to a high of 20 degrees starting off in the low model in the Yamhill, and then increasing to the entire Yamhill and then portions of the Tualatin when you get into the higher climate change scenario. So you'll see this pattern over and over again, that of the Yamhill being higher in temperature than the Tualatin, and also of the increasing stream temperatures as the climate scenarios increase. So we're looking at the change in mean monthly stream temperatures. This is the absolute change in degrees Celsius from the historic model. And you can see that the overall change is more extreme for the upper reaches of the Tualatin. While the Yamhill has warmer stream temperatures overall than the Tualatin, the upper reaches of the Tualatin are going to see more absolute change in stream temperatures. Here we're looking at the mean yearly days above 20 degrees Celsius. So we start off a low of 18 days in the historic model and then in portions of the low climate change model. And we end up with a maximum of 98 days above 20 degrees in the high climate change model in the Yamhill Basin. You can see the same pattern of the increasing stream temperature as the climate change scenarios increases, although that effect seems to be muted for some reason in the low climate change scenario for the Tualatin and portions of the Yamhill. Another way to look at that information is at the basin scale. So you're seeing the same pattern of increasing temperature as the climate scenarios increase, and the higher temperatures being found in the Yamhill Basin. So one of the main drivers that we found so far in analyzing this model for stream temperature is air temperature. And you can see here we've got stream temperature, simulated stream temperature and simulated air temperature, and they're seem to be very nicely related linearly as well as temporally. Interestingly enough, we found that our stream temperature model isn't sensitive to land cover changes, and that land cover hydrology changes that are occurring because of land cover changes don't seem to have a significant effect on stream temperature either in relation to air temperature. We suspect, though, that there are parameters of land use effects or land use change that would change or affect stream temperature, and we're trying to tease those out of the model to see if we can figure out, number one, what are the other parameters that do affect stream temperature besides air temperature, and to what degree do they explain the variation in stream temperature. So one of the things we were trying to examine was hydrology. So if you change, if you augment flow in low flow times of the years, you would think that would decrease stream temperature, or if you do some land cover modifications like shading, that would decrease stream temperature. But I didn't show these results here, but we found that our model was pretty insensitive to changes in flow. When we changed these land covers drastically, we found that flow was changing, but stream temperature wasn't changing. But this model's been used to simulate stream temperatures in places like the Sierra Nevadas, and they found in that study, Ficklin et al. Found in that study that there was a direct relationship between hydrology and stream temperature, and the component of hydrology that was most related was snowmelt, or the timing of snowmelt. And I guess our study area isn't really driven by snowmelt. The hydrology isn't really driven by snowmelt, so maybe that's why we're not seeing that difference. And I mentioned shading. There's no explicit parameter for shading in this model. There is something called a bulk heat transfer coefficient, which is supposed to correspond to shading. We are currently trying to figure out if that coefficient actually does correspond to shading. If it does, how well does it correspond, and can we then manipulate that parameter outside of the built model to better model changes in land cover or increases in shading on streams. So overall, we're just trying to pull out information about the different parameters that are supposed to be controlling stream temperature in this model, that are cited to control stream temperature in this model, and seeing in relation to air temperature how much of the variation in stream temperature do they account for. So our conclusions are basically, if we believe this model, climate change is going to have a significant impact on stream temperatures in the Tualatin and the Yamhill basins. The Yamhill Basin is going to have the worst absolute conditions, but the largest change in temperature is going to come in the upper reaches of the Tualatin. We did look at another model that our cohorts in Heejin Chang and here at Portland State created of the Tualatin that was built with a different program but used similar land cover and climate change scenarios, and we found that our results fell within the range of the results of that model. So we want to do a kind of similar analysis with the Yamhill model that we built to see if it's falling within the range of other models that have been built. But if we believe this model, the current results are suggesting to us that climate change alone, and in particular air temperature rises, are going to impact stream temperature significantly, and that the fact that it's largely due to air temperature is going to really make it difficult for us to mitigate any type of or use any type of management options in the future. Thanks.